This is Dr. Mimi Lamb from Metro Health Medical Center, and I would like to describe a clinical tool called the Urine Anion Gap and explain how we use it. Urine contains equal numbers of anionic and cationic charges in addition to its many uncharged molecules such as urea and creatinine. The cations include sodium, potassium, ammonium, and a bunch of miscellaneous things that we call unmeasured cations, while the anions include chloride, bicarbonate, and unmeasured anions. In other words, in the urine, the electrochemical balance can be expressed by saying that the concentrations in milliequivalents per liter of sodium plus potassium plus ammonium plus unmeasured cations equal the concentrations of chloride plus bicarbonate plus unmeasured anions. Since urinary bicarb is normally 0 and urine ammonium is complicated to measure, if we ignore the unmeasured anions and cations, we can rearrange this formula and create a so-called urine anion gap, which is simply the urine sodium plus potassium minus chloride. And although it is a gross oversimplification to think that sodium, potassium, chloride, and ammonium are the only ions in urine, the urine anion gap can give a very rough qualitative indication of urinary ammonium excretion, which in turn reflects renal tubular hydrogen ion secreting ability. So let's see how to use the urine anion gap by looking at 3 simple examples. In a normal state, urine ammonium is present in small amounts and the urine anion gap is close to 0. Here, in milliequivalents per liter, the urine sodium is 50, potassium is 20, chloride is 65, and ammonium is 20. And the urine anion gap, sodium plus potassium minus chloride, indicated by this small area, is plus 5. In the normal response to a metabolic acidosis, there's a lot of ammonium generated, and the urine anion gap will be a large negative number, usually between minus 20 and minus 50. Here, the urine sodium is 40, potassium is 20, chloride is 110, and ammonium is 80. And the urine anion gap, sodium plus potassium minus chloride, is minus 50, reflecting the synthesis of ammonium. And in our third example, we have a distal renal tubular acidosis, or RTA, with impaired hydrogen ion secretion by the distal nephron. This in turn means impaired bicarbonate reabsorption and decreased synthesis of ammonium and titratable acids. Now the urine sodium is 40, potassium 20, chloride 65, and ammonium is inappropriately low at 10. Also, because of the inadequate hydrogen ion secretion by the distal nephron, there is some bicarbonate in the urine, and the urine anion gap is only minus 5. In other words, the relatively small negative value of the urine anion gap reflects the inadequate hydrogen ion secretion, incomplete bicarbonate reabsorption, and impaired ammonium excretion seen in distal RTA. So in summary, the urine anion gap is a clinical formula that helps us to determine whether or not the kidney is responding appropriately to a metabolic acidosis. It can be used as an estimate of urinary ammonium excretion and therefore of renal tubular hydrogen ion secreting ability. An appropriate response to an acidosis consists of lots of hydrogen ion secretion with complete bicarbonate reabsorption and increased formation of titratable acids and ammonium. With a metabolic acidosis, the urine anion gap should be minus 20 to minus 50. If it is not, as in distal RTA, the urine anion gap provides an important clue that there's a problem with renal hydrogen ion secretion, and that is why the urine anion gap is so helpful to us.